This is Chapter 3, Section 1. We're starting on probability. So, probability is a chance of something occurring, and to figure out probability, you have to do probability experiments, which are well-defined outcomes or results when you do it, essentially. So, an outcome is a result of a single trial, right? So, the event is a set of outcomes, which are either simple or compound. So you can't break it down any further. It's a simple event. Two or more simple events is a compound event. So, because what you need is the sample space, which is all or the complete set of all the possible outcomes. Because in order to figure out a probability, you need to know how many it is out of. Because if you don't know how many there are, how do you know what the probability is? So we'll take, for example, flipping a coin 4 times. Each flip of coin is either heads or tails, assuming it's a fair coin, which means each side is equally likely. And fair is a standard probability term, meaning equally likely, equal probability. So an outcome here is a flip of a fair coin, right? Okay, so we'll bold and blue that. There we go. Okay, so the event here is 4 flips of a fair coin. Okay, so how do we explain this as terms of simple and compound? Well, the simple event essentially would be a flip of heads, right? That would be a simple event. I mean, it could be heads or tails, obviously. But the compound event could be, for an example, heads, tails, right? But that's only one possibility, right? There's many possibilities of flipping the coin 4 times, right? So essentially what we want is 4 flips of a fair coin, right? Okay. So if we want to do the sample space, it's a combination of heads and tails. So either all heads or all tails, or some combination thereof, essentially, right? So, right, so you have all heads, all tails, right? You have 1 head and 3 tails, 1 tails and 3 heads, or 2 tails and 2 heads, right? So that makes 16 possible, right? So the sample space is 16. If you think about it, there's 2 possibilities, heads or tails, and I'm picking 4. So that gives me my sample space. So if I ask the question of what's the probability of getting tails 4 times in a row, it's 1 out of 16. What's the probability of getting 1 head and 3 tails? That's going to be 4 out of 16, right? Fractionally. So if I write the sample space in proper notation, it would be the squiggly brackets, and you'd write T, T, right? T, T. Yeah, writing's bad. Dot, 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 all the way to heads, 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 right? That would be the proper notation, the way to write it. You just put all 16 of those between the brackets, essentially. Okay, so how do I know what's in the sample space without trying to use logic, basically, or IQ, to list out all of them, right? You use the fundamental rule of counting, which basically says you multiply. So let's say I have the blood, so bags. They have A, B, and O are the basic types of blood, right? Which are Rh factor, positive or negative, and you have male and female blood, right? So, if I wanted to figure out how many blood bags there are possible, I could again do logic and list out like I did before, right? So let's do blood bags equals. Okay, format color blue. Alright, where did that go? That's on the wrong page. Picture, layout, square. Okay. So I could just use logic and just figure it out by using pattern recognition. I could do a tree, right, and that gives me the sample space. So this is the sample space here, right? Okay. But if I don't necessarily need to know the individual ones, I just want to know the total, I don't need to do logic or a tree, right? I could just use the fundamental rule of counting, okay? So the number of blood bags, essentially here, is going to be 4 times 2 times 2, And why is that? Well, I have 4, 2, and 2 as far as categories, which gives me 16 possible blood bags, essentially, right? Okay, so essentially, if you want to list it out, right, blood type times RH factor times gender is going to give you 16, essentially, right? Which you can see all through here is my sample space. Okay, so basic notation, the uppercase P denotes a probability, right? Any other letter, A, B, and C, those are the events. Typically, you can write those as words also. Just don't use P. And you'll see a lot of times I'll use whole words for those. So if I say P of A, that denotes a probability of A occurring, is essentially what I'm saying there. Okay. Equally likely events are basically the ones that have the same probability or equal probability of happening, right? Some standardized vocabulary words, you know, certain, likely, 50-50, unlikely, and impossible. So first off, all probabilities must be between 0 and 1 inclusively, right? Can't be more than 100% or less than 0. It's not possible. The sum of all of the probabilities must add up to 1. 0 is certainly possible and 1 is certainly possible. Okay? Unlikely means low, and likely means high probability, right? I can't spell. There we go. All right, so low and high is a subjective term. You'll notice some textbooks in high school can actually give you some kind of breakpoint value of like 90% or 95%. That's not what you should do. Likely and unlikely are subjective as to how high that is. And if they are equal, approximately equal, right? Okay, then it's 50-50. Okay, so if it's approximately equal, it's 50-50. Does it have to be exactly? No. Okay, but again, these are all just basic terminology. Okay, so let's take a look here. So if I'm on a plane crash on a national carrier, it could happen, but it's very unlikely, right? If I want to win on black on the roulette, well, it's pretty close, but it's not necessarily black and red in roulette. There's also the zeros, which make it green. So it's close to 50-50, but not quite. But we'll say it's close enough for a 50-50, essentially. Okay. Surviving a 5,000 foot parachute jump without your parachute. I'm going to say that's probably impossible. Whoops. There we go. You survive a plane crash, but you don't fly on planes. Well, we'll assume that the plane is not going to come out of the sky and hit you. So we'll say you'll certainly will, right? And if you flip a coin 1,000 times, you get between 450 and 550 heads. Well, that's about what it should be, somewhere in that range. You could get more or less, but that's pretty likely that it's going to come up with that range of answers, essentially. You could get out, but it's very unlikely. Right? So that's your basic vocabulary and symbolism. Right? So, law of large numbers. So, let's say you were flipping a coin. If I flip it once and get heads, does that mean heads is 100%? If I flip it 3 times and I get 2 heads and 1 tail, does that mean it's 66? No, essentially what happens over time with probability is you increase the number of trials, it increasingly gets closer and closer and closer, the true probability, within increasing numbers of decimal points. So it might be close by 1 decimal point, then 2 decimal points, then 3. So it's a question of how close do you want to be. So as you increase samples, it increases accuracy by decimal places, but never quite gets there perfectly in most cases. The coin you might get there, but the next new trials might be off again. But that's typically what you have. So with law of large numbers, that works for both classical probability and empirical probability, not necessarily subjective, right? So there are 3 types of probabilities, right? There's what's called theoretical or classical. I tend to lead on the theoretical, right? Which means there's a theoretical answer it should be that you're working towards. And then there's empirical, which is when you use frequency distributions to figure out based on data what the probability is. And there's subjective or personal, right? Which is you're using opinion, basically. So you have one that's opinion, and then 2 that are calculated. So calculated and calculated. Except this one has a real answer that you're working towards, right? because it's the number of ways it occurred over the total number, right? So there's an actual sample space. There's an actual sample space you can calculate, right? Like the heads and tails one. So if it's an empirical one, there is no sample space. You're just using a frequency distribution. There is no sample space. Okay, so we don't actually. There is no theoretical probability that should happen essentially. Okay, so if I look down here at my 3 examples, right? First is playing the lottery, and this lottery has 60 balls that are 30 red and 30 blue. So if I guess on a number, what's the probability of winning? Well, my ball's going to show up twice, once for red, once for green, right? So that's 2 out of 60. So that is a theoretical probability because there's an actual probability and there's an actual sample space I can work towards, right? Is the probability actually 2 out of 60? Well, in practice, no, you're going to play, you're probably going to lose. Play again, you're probably going to lose. And if you played a whole bunch of times, eventually you would get to 2 out of 60. If you played thousands and thousands of times, it would eventually work out at 2 out of 60 or 1 out of 30. You don't need to simplify fractions for this typically, right? Is it ever going to get to perfectly 2 out of 60? No, it'll come increasingly closer and closer and closer decimal-wise to that actual answer, but never actually truly gets there. What's the probability I'm going to wear a suit tomorrow? Well, that's opinion, isn't it? There's no way I can calculate that, really. So I'm just using an opinion as to what I believe that answer will be. Okay, let's say I survey 1,010 people and asked them if they smoke or not, and 202 said yes. Well, that means 202 out of 1,010 actually smoke, right? Is there some kind of theoretical probability I can compare that to? No. I'm using frequency distributions, right? I went out and did a survey, made a frequency distribution, and I calculated it. So that is an empirical probability, essentially, because there is no theoretical to work towards, so I'm just using frequencies, and this actually changes over time, right? This changes over time because each decade people smoke more or less, right? You can do the same thing with car accidents in your town, right? Figure out the number of car accidents in your town. It'll probably go up over time as the population grows. That also changes, right? Or do I don't know, death rates in the hospital. That'll probably change over time, right? But this never changes. So if you played the lottery, no matter how many times, the probability does not change. Okay. All right, so that's the 3 types of probability. So compound events is, as we talked about, 2 or more simple events, correct? So we need to get into the symbolism of compound events. So you don't typically say and and or. You can, but typically you don't do that. Typically you're going to use 2 different symbols. This symbol here, which is the intersection, or you're going to use this symbol here, which is the union. Okay, let's make those blue. Format, color, blue. And we'll style that as text. Okay, perfect. Okay, so you can think of it this way, essentially. If I have a Venn diagram, right? Venn diagram, I have 2 circles, right? Circle A and circle B, right? Say A and B, right? If you're out driving, eventually 2 roads meet, correct? Road A, road B, and there's an intersection. So that is the intersection where it's both, isn't it? Correct? So and is both. Okay. Or is union, which is just everything together. So if you take all of it together, that's a union, right? Like a labor union, you come together, put them together, union, right? So typically you don't use the words and or, you use those to represent those essentially. So I always remember union like unionize, you come together. I remember intersection like traffic intersection, it's the part where they just have in common, versus union, just everything together essentially, right? Okay, so let's we'll copy those. We'll paste that. There we go. Okay, so let's do this in a very basic level. So A is 1 through 5, B is 4 through 8. So determine the following, the union. So put these 2 together. Okay, so if I put all those together, I'm just essentially going to get 1 to 8. Notice I didn't repeat the 4 and the 5, right? Because those would be the intersection, right, of the 2. So if I drew the Venn diagram again, right? If I drew the Venn diagram, right, the 4 and the 5 would be in here, correct? right? Versus this would just be 1, 2, and 3 over here, right? And then 6, 7, and 8 would be over here, correct? So I don't write 4 or 5 twice here, right? So what do they have in common? They have 4 and 5 in common, don't they? So intersection, which is this symbol right here, which means and, right? So it's in A and it's in B, right? A or in B. Or, remember from high school proofs and geometry, or means one, the other, or both, doesn't it? Right? Okay. So let's talk about compound events here. So this is the sample space of all the dice combinations if you roll a die that's white and red, right? So you get 36 combinations here, right? So I want to know if B is the event of getting a 3 on the white die, and A is the event of getting a red, even on the red die. So even on the red die is this one, the 2, the 4, and the 6, right? And then getting a 3 on the white die is this one right here, right? 3 on the white die. So either way, this is out of 36, out of 36, right? Out of 36, and out of 36, correct? Okay, so P of A is going to be evens. That's 6, 6, and 6 is 18, right? 3 on the white die is these 6. So if I want them together, what's together? Well, this one is both, this one is both, and this one is both, isn't it? So that's 3 that are both, right? Because they have to be A, which is even on the red die, and B, which is 3 on the white die, which is both, right? So if I want to do or, can't I just add 18 plus 6? No, you cannot do that, because if I do that, I'm counting these ones twice, aren't I? Because I'm counting them this way, and I'm counting them this way. I'm counting them twice. So you have to subtract out the overlap, right? So in fact, I get, so that'd be what, 321 out of 36? Right? Okay, so always do the and before the or, because you have to subtract over the overlap, so you don't count it twice, essentially. Okay? All right. So those are our simple events and our compound events, essentially. That's what we went through there. All right. Complement doesn't mean, hey, that's nice shoes. That's not what we mean, right? So complement is if something occurred or something did not occur, is essentially what we're saying here, right? So we're going to bold and blue. There we go. Okay. So you can denote a complement in a couple different ways. Two of the most common ways are this, where they use the bar above it and then the little asterisk. So when I do calculations in Excel later on, I use the asterisk because I can't put the bar above it. But the modern notation is this one. This one. This is the old notation, okay, which is useful if you're typing on a typewriter or an Excel or something because you can't get that bar above it. But this is the modern notation, right? So it's read as a naught, essentially. Or I'm not an A, or whatever the case may be. Okay, so if you look at a book for the rule of complement, right, you'll see a Venn diagram typically, right? So if I'm either something or I'm not something, correct? So 1 minus P of A. So if 40% of the time I'm A, then obviously 60% of the time I'm not A, correct? Right? And if I'm 20% here, I'm 80% here. If I'm 10% here, I'm 90% here, right? So whatever the case may be, right, it's 100% total, right? Okay, so A plus not A equals 1. So depending on what book you pick up, you're going to get 3 different variations of the complement rule. The first one is the one I did, which is this, right? Another way to put the rule is A is the same as 1 minus not A. And not A equals 1 minus A. So these are 3 different variations of the same rule. Are they somehow different? No, depending on which book you pick up. It's whatever one the author decided they liked better, or they're used to, and they just picked one of them. They're all algebraically the same, so don't get thrown off by that. Okay. All right, so we have, 2010, 25% of the population was over 65 years of age. Determine the probability a randomly selected person from the Japanese population would not be over the age of 65. Write the probability in words and write the probability in symbols using O for the event the Japanese citizen was over 65 years of age. Okay, so let's do a little symbols here. So we're going to do this and put that up there. So we have P of O. Right, so we'll put an O in there. Equals, and we'll copy this. Alright, copy, paste, and we'll put the bar above it for not O, right? So if this is 0.25, then the other one is 0.75, correct? Okay, because we're saying 25% of the Japanese population is over 65 years of age. So probability. So let's go to text here, style text. Probability a Japanese citizen is over 65 years of age, right? So you might want to do this and just copy it, right? And just go to here and paste it, right? And put is not over 65 years of age. And that would be incorrect. Because what about the 65-year-olds? They're not in there, and they're not in there, correct? Is 65 years of age or younger. So this now includes everybody, basically. So what I'm trying to get at here is when you do these, make sure you include everybody, right? Or everything, whatever the case may be, because we need this to add up to 1, right? If this doesn't add up to 1, you have an issue. So you need to make sure these are inclusive categories, essentially. Okay? All right, that's the end of the first part.